Well, thank you very much. It's a real honor to speak here at Elm Europe. Because of some problems about going back and forth with different screens, I'm going to, at the last minute, invert some things in the talk. So my talk is about bringing LaTeX to the browser. So for those of you who have not seen LaTeX before, there it is. That's what it looks like. That's the output of LaTeX. So it's something that mathematicians, physicists, computer scientists, people in certain technical fields use to write research articles, to write class notes, and so forth. And for a long time, there's been a very good technology for bringing LaTeX to print, to making PDFs, but there are certain things that are missing when you want to bring it to the web. So that's what I would like to talk about today. Maybe just a real quick live demo to show you that this actually does work. It's not just all fake. So here's a little demo app. I'm going to, maybe that's not the right one. Oh dear, just a second here. 1 second, there we go. Yep, that's the right one. Okay, so on the left-hand side, you see LaTeX source text. So, for example, right, so it doesn't, there, yeah, I can barely see it. Maybe it's better if I highlight it here. So you see various sections. So that's a section heading. Over on the right, you see one MiniLaTeX. So one of the things that LaTeX does is it automatically numbers sections. Above that, you see a little table of contents. So it also will construct that for you. You notice that you have some very nice equations there. Here's the first one. It's labeled as equation 1.1, and you'll notice in the paragraph above that you can, say over in the rendered part, there are equation numbers that refer to that. So you can have internal cross-referencing in your document. You can display images. Something that I put in my little project, which I call MiniLaTeX, is the ability to display an LA. And if you want to write educational materials to help people learn Elm, it's very nice to be able to have text and an LA all embedded together. So there it is. You can run it. It seems to be working okay. My number is a little bit offset, but that's okay. So that's what LaTeX is. It's a markup language like ASCII-Doc or Markdown that is designed for people that have certain technical needs. And so let me now do the real thing here. So I'm not really used to this. I'm used more to chalk and blackboards. We'll see how this goes. So the idea is to bring all of LaTeX to the browser. And to do that, we have to make something called a parser that will analyze the LaTeX source text and eventually produce something nice on the screen for you. And the real website to look at this is knode.io. That's, for example, I taught a course in quantum field theory, and my notes written in MiniLaTeX using an Elm app are at that site. Here is a little snippet of LaTeX. And here is its rendered form. It's an integral formula. So what you see on the left might look like gobbledygook, but if you get used to this, and it really takes very little time, you become very fluent in it. In fact, mathematicians will often send each other emails with this stuff in it and not rendered, but we can all read it and understand what it says. Here's another little piece. When rendered, it looks like this. It's a numbered theorem. So one of the things that LaTeX does is it numbers things for you. You can cross-reference those and so forth. So there are actually two parts to LaTeX. There's the stuff between dollar signs for equations and formulas, and there's the rest, the stuff outside. Now, as I said, there's a good technology for doing print and PDF, but for the web, there is a good solution only for number one, the inner part of LaTeX between the dollar signs. And there are various programs that you can use to do that. MathJax.js is one. Notice the JS on the end there. And but unfortunately, up to this point, there hasn't been a really good solution for the rest of LaTeX. So what I want to show in this talk is that Elm can do part 2. By the way, there are batch processing things that will turn LaTeX source into something you can post on the web, but it can't be run in an interactive live editing situation, and that's what I'm looking for. So we already did that. Let me talk about my first, and I must say, misguided attempts to do this. For some reason, I started off with a language called ASCII-Doc, kind of like Markdown. And I developed an extension to it called ASCII.LaTeX. And it's still out there and running, but it was a bolted-on solution, and like most bolted-on solutions, it didn't, it had a lot of rough edges. It was also based on regular expressions, and as we'll see later, there are theoretical reasons why regular expressions simply cannot do the job for you. It doesn't matter how clever a programmer you are, you just can't do it. The other problem I found is that, well, I started off with Rails, and I got things running, but after a while my code kind of looked like this. It was a total Rube Goldberg device. I couldn't maintain it. In fact, now I don't even want to think about it because that might cause it to break. So I went to a client-server architecture with Elixir on the back end, Angular 1 on the front end, same story, Angular 2, same story, and then I gave up. And I began to think, there must be a better way to do this. And I really liked what I had been doing on the back end with Elixir. And that's a functional language, so I thought, well, maybe I should use a functional language at the front end. And somehow I learned about Elm, and after a couple of false starts, I built a little prototype. That was in about May of 2017. And, well, my wife told me that I was very isolated in my work and I needed to get out of the basement and talk to people. So I came to Elm Europe last year and learned a great deal. I had a couple of really important conversations, one of which was with Evan. And I described, I was still working with ASCII.doc at that moment. I wanted to try to build a proper parser for it. And he said, well, why don't you take a look at Elm parser tools? So I did, and when I got home, I started thinking about this. And then one day I realized that I was doing everything wrong. Instead of trying to bolt something onto ASCII.doc with a better parser, I could actually write a parser for LaTeX. And that's the right thing to do because my intended audience consists of people who already know LaTeX. So, how am I going to get them to adopt a solution if they have to learn something new? So here's the problem. We have LaTeX source text, and we want to render it into what you see at the bottom. Now, you can't do that directly. You've got to go through an intermediate step of making what's called an abstract syntax tree. Okay? And that's going to be some kind of a data structure that expresses a grammatical understanding of the source text. Once you have that, it's quite easy to write the code that you need to render it into HTML or anything else. I even wrote something to render it back into LaTeX, which seems very stupid, but it actually has some uses, only one of which is for testing, because you see, if you start with something, you make an AST, and then you transform it to LaTeX and you get the same thing, then you know you've done things right. You've implemented the identity function. Okay, so what the heck is an AST? Well, we're going to think about this in the context of English. I'm sorry, I should be doing it in French, I suppose. We'll look at an English sentence and we're going to analyze it. We'll analyze the sentence, John ate the cat. And if you've diagrammed sentences in high school, this will all seem very familiar, but the idea is the following. A sentence can have many forms, one of which is a noun phrase followed by a verb phrase. And a noun phrase can be, well, it could be a name, it could be an article followed by a noun, but let's choose the first alternative. And the name could be John, it could be Fred, it could be Mary, it could be Sue, it could be lots of things. Let's choose John. So what you see here is the beginnings of an abstract syntax tree for John ate the cat, a so-called parse tree. And the colored nodes are the ones that have children. Those are called non-terminal nodes. And John, which is in black and white, is a terminal node. John has no children. So let's go back to the verb phrase. Again, there are many forms. Let's just choose a standard one, a verb followed by a noun phrase. And we'll continue applying some sort of mysterious rules, deriving more and more children until we can't go any further. So for the verb, we'll choose ate. For the noun phrase, we'll choose an article followed by a noun. So it's not yet a set of terminal symbols, but the article we're going to choose is the. It could have been a, but we'll choose the. And for the noun, we could choose cat, we could choose tree. There are various things we could choose. Let's choose cat. So there is the syntax tree, or the parse tree. It has terminal and non-terminal nodes. And if you read the terminal nodes from left to right, you have the original sentence. And the non-terminal nodes and the way they're linked together, it expresses our understanding of the grammar of that sentence. So there's an intimate relationship between syntax trees and production rules. Here are the production rules for the syntax tree that we just saw. There's the tree. And you can understand practically everything by just looking at the colors. So S, which stands for sentence, can be derived to noun phrase followed by verb phrase. So there's a little rule that tells you how to construct the children of the S node. NP is noun phrase, VP is verb phrase. Same with noun phrase, except for a noun phrase, I don't know if I can aim this thing. For the noun phrase, there are two alternatives. It's like an Elm union type. It could be a name or it could be an article followed by a noun. So you construct syntax trees by applying these rules, and you stop when you reach terminal symbols, when you have no more non-terminals to transform. And once you have that technology, you can generate lots and lots, actually infinitely many, grammatically correct, if ridiculous, sentences. So Mary ate the dog, John ate the mango, Fred likes the kangaroo, etc. Now, a very important point is that the formal grammar that we're looking at here is entirely contained in the production rules. So I said at the beginning that we have to parse LaTeX. So what's the relationship between productions and parsing? Am I just going on some tangent? Well, we're not, because, and let's look at it this way. If we start with an initial non-terminal node S, we apply the production rules, we get the AST and the sentence. Parsing is the reverse of that, or the inverse. We take a sentence and we go backwards and produce an AST. That sounds like a harder problem, and it is. So parsing is the inverse operation for production. So it's time to talk about LaTeX now with this prelude. Let's try to see, let's look at an abstract syntax tree for this little piece of LaTeX text. So we're going to begin with a non-terminal node. LL stands for LaTeX list. It corresponds to that whole thing there, that whole unparsed blob of LaTeX. Applying some as yet unspecified production rules, LL derives to 3 child nodes. MA stands for the macro, strong, curly brackets, Newton. Okay, so that'll just, when rendered, it will be Newton in bold text. The next child is LS. That is going to be a LaTeX string. It'll just be says. And then finally, EN for environment will be all the rest. It'll be a so-called theorem environment in LaTeX. So we continue deriving things using our as yet unspecified rules. The macro consists of its name, strong, and its arguments, which is the word Newton. The string ls derives to says. The environment is the most interesting thing. Its children are, first of all, the name of the so-called theorem environment, and its body, which is a list of things, and that's just all that stuff in green. And then you continue. That derives to actually a list of, I think it's 5 things. There is, if you point to it, there is a little string, an inline math element, another string of English text, another inline math element, and so on. So that's an abstract syntax tree in LaTeX land. And now we want to think about how we can do this in Elm. So an AST is going to be some kind of a value. And the question is, what kind of a value is it? Well, it has to have a type. So let's dream up a name, LaTeX expression. And let's dream up a definition. And there it is. It's a union type with various components. And they all have a payload or a parameter. And if you look at it, you notice that a LaTeX expression has as components things that are themselves LaTeX expressions. So it's a recursive union type. And this was actually almost the first thing I did when I embarked on the project. I I didn't have a parser code, I didn't have a grammar, but I wrote down the definition for the AST. So let's look at how Elm represents the AST for what we had before, our little tree for our little snippet. There it is. And once again, if you just follow the colors, you can understand it. But that's clearly an Elm value of type LaTeX expression. Okay, so how do you build the parser? Well, the usual way to build a parser is to start with a grammar. The problem is that there is no written grammar for LaTeX, so we have to reverse engineer one. And to do that, it's useful to think at least about what kind of grammar you have. I'm going to speed up now, folks. So there is a hierarchy of grammars. Regular expressions is the lowest in the hierarchy. It's the least capable of all. It can't even parse arbitrary balanced parentheses. That's what I was using for ASCII.LaTeX, and so, it can't work. Flipping through, there is a hierarchy of grammars. It turns out that MiniLaTeX is a context-free grammar. Is a context-sensitive grammar. So it's not the kind of thing that the usual tools like Bison can work with. But let's try to build the parser anyway. That's me when I thought, oh my God, this is going to be too hard. But it turns out there is a technology of parser combinators that comes to the rescue. It's built on the idea of having certain elementary parsers that can gobble up a certain bunch of characters from the input stream and recognize them, and maybe turn them into something or maybe not. So symbol paren will, if it's looking at the input stream and it sees a left paren, it gobbles that up from the input stream and says, yay, I've parsed it, success. Otherwise, it says failure and game over. Spaces is a parser that will gobble up 0 or 517 spaces, and then it stops when it comes to a non-space. Float does the same thing with float, with a floating point number, but it will give that floating point number back as a value. Combinators are ways of taking the parsers that you already have, maybe these elementary ones or maybe ones that you've built up, and combining them in various ways, like putting them in a sequence using pipelines, or the one-of combinator means you have a list of parsers, you try the first one, if it succeeds, yay, I'm done. If not, you try the second one, and so forth. So let's illustrate this in the case of parsing 4216, a text representation of a number, of a point in the Cartesian plane. So there's the production that corresponds to that point. A point is a left paren followed by spaces, followed by a float, and so on. And once you have that production, you know how to generate points in the plane. There's the parser that I'm going to explain in just a minute. It's straight out of the documentation for Elm parser. And it's going to create a structure of type point. It'll be a record with two fields, an X and a Y value. And the parser is like a little machine that gobbles things from the input stream and processes them using elementary parsers and whatnot. So the idea is that you first of all try to gobble a left paren. If you succeed, you then try to gobble spaces. Then you try to gobble a float, and so forth. Pipe dot means parse it, gobble it up if you can, but ignore what the value is. You don't care. You forget it. Pipe equals means gobble it up and convert it into what value it should be converted to, like a float, but remember it. So this parser, the so-called parser pipeline, will, if it succeeds, it will have created two floating point numbers, which are then fed to the point constructor, and what comes out is this Elm value. So, reading across the right-hand side of the production is like reading down the code for the parser. So there's an intimate relationship between these production rules and parser combinators. Let's take a quick look at how this works out for MiniLaTeX. So there's the top-level production. It can be a LaTeX expression, can be a display math element, $ signs enclosing arbitrary math text, Same with inline math, except it's single dollar signs. Words, okay, we can do that. A macro, like \strong curly brackets Newton, consists of the macro name and 0 or more arguments. A LaTeX list is a list possibly empty of LaTeX expressions. And last is the environment production. And it's different from the others. You notice that because it has 2 colors on the left. That's the signal that this is a context-sensitive grammar. So env is a non-terminal symbol. Env name stands for some terminal symbol like theorem or proof or joke or quote or whatever. Okay? So that the stuff on the left produces a begin-end pair, which is named, and enclosing an arbitrary LaTeX expression. So I think I'm going to take my few extra minutes, and there won't be time for questions, but at least we'll be able to finish that way. So let's look at the top-level parser. There it is. I've just repeated with better colors the production for a LaTeX expression. And there is the parser. And notice that reading across the right-hand side of the production is like reading down the code for the parser. I've used the one-of combinator instead of a parser pipeline. So that means I first see if I can gobble up a display math element. If I can't, I try inline math. If I can't do that, I try a macro and so forth. The last one is the most interesting one, the environment. So the environment parser, if you went back and looked at the grammar, the production for that has LaTeX expressions on the right. So that means it's a recursive thingamabob, and that's why we have to put lazy in there. If you don't have recursion, none of this is interesting and none of it works. So the parser actually is a very small piece of code, 334 lines. The macro parser, for example, it looks like this. There's a little macro that we're going to try to parse. \LA, first argument is the ID, second is the label. There's the production, there's the parser, there's the output. And once again, reading across the right-hand side is like reading down the definition of the parser. And the important thing is that these things, unlike regular expressions, are readable and therefore refactorable. And if you're going to build things up from the ground, starting from 0, it's very important to have stuff that you can go back and read and understand and add to. So to wrap things up, let me say a few words about rendering, because remember there was this two-step process. First create the AST, then render the text. So rendering turns out to be very easy once you have the abstract syntax tree. All you have to do is write one rendering function per non-terminal symbol. And I actually have several renderers. The first one, which renders into string, a big piece of HTML, is 719 lines. Later, with a suggestion from Evan, I rewrote the renderer to produce HTML message. That's a little bit longer. And for stupid reasons, well, actually good reasons, I wrote a renderer that renders it back into LaTeX, and that's only 72 lines long. So here's the top-level renderer. Notice it renders a LaTeX expression. Notice the parameters are LaTeX state, which is something we'll talk about in a sec, and a LaTeX expression. And then there's just a long case statement with one case for everything on the right-hand side of the production for the non-terminal symbol LE. So, cross-references, you also have to do those. For that, it turned out to be necessary to create the right kind of abstractions, because otherwise you get horrible code that you can never maintain. And what turned out to be the right thing was something called an accumulator. It takes a state and a list of things of type A, produces a new state and a list of things of type B. That's about 130 lines of code. So, lessons learned. One is it's sort of speaks to one of Evan's comments. Elm is described as a simple language, and it is. But that doesn't mean that it's not powerful. In fact, in my opinion, it has CS superpowers, one of which is the Elm parser. I mean, there are many others. Another is that Elm has the mojo to find the right solutions to your problems and the right abstractions. So for me, the right solution was to write a LaTeX project, not to bolt something onto an existing markup language. So, everybody will find their own right solutions and right abstractions, but that's what it was for me. Finally, there's an amazing community without which I could not have done this project. And I'd like to thank Evan for a number of critical suggestions. Really big thanks to Elias Van Peer, who helped me with the Parser when I was writing that, and also with a very important optimization to the renderer. And Luke, saved my bacon at the very end when I went to a different rendering scheme with some custom element code. And finally, everybody on Elm Slack. So thanks, everybody. Thank you.
Thank you so much, James.
Thank you.
We'll take like 2 questions.
When you compare I wanted to ask about the power of Elm tools and Parser.
Yes.
Which level of Chomsky hierarchy is it able to parse?
Yes. Well, I think actually, I used it in the next to the highest level, which is context-sensitive grammars. So it can certainly do that. I believe it will do recursively enumerable, but I have not tried that. Do you know, Evan? Yeah. Yeah.